Hi there, welcome to this lecture series on matrix algebra. This is lecture 17 and the topic is a brief review of complex numbers. So we'll go through definition of complex numbers, their basic properties, vectors and matrices with complex entries. Let's get started. So a complex number, let's use Z to denote it, and the set of numbers that are complex is this fancy C for complex. So a number Z in C can be written in the following form: Z equal A plus IB. Okay, and this I is this magic symbol to denote that it's the so-called imaginary part. So here, the A is a real number, and the B is also a real number, but it has the I in front of it. So the part B is called the imaginary part, which we write B equaled imaginary. We take IM of Z to say that's imaginary part of Z. And then, of course, A is the real part, and it's denoted as RE, real part of Z. Okay, an obvious example. Let's say Z is now 2 minus 3i. Then the real part of Z is 2, and the imaginary part is -3. So there is a polar coordinate. So in the polar coordinate, you have these two vertical axes. The horizontal one represents the real part, and the vertical one represent the imaginary part. A number A plus IB would have the axis in the real part direction with length A, and the axis in the imaginary part, it will have length B, and the Z would be the point that takes the coordinate AB. And then in this polar coordinate, we can find a unique value we call radius, and which we denote it by R. That will be the length from the origin to the point C. So that would equal to square root of A squared plus B squared. And then the line from the origin to Z would also form an angle with the real axis, and the angle, the positive direction for this angle is indicated here, the counterclockwise one. Okay, and the angle theta is defined on the interval from -pi to pi, so it will be -pi here, come to 0, and then all the way to pi. When it's pi, it meets the -pi. And if we use R and theta, given the R and given the theta, you see that it uniquely determines a point in this coordinate, right? So you can first draw the length of the R here, and then you rotate it theta by the theta angle. And then the relation between this notation R and theta with the original notation we have here is the following. So the value A here will be this length here, so that will be the cosine of this theta times R. So it's R cosine theta. And the value B will be the length from the point Z down to like a vertical perpendicular projecting down. So that length here would be the R times the sine of theta. Okay. Then the absolute value of Z, which is just the R here, the positive square root of A squared plus B squared. It also has other names. It's also called the modulus of Z, or the absolute value of Z. And this angle theta is called the argument of the number Z, and also sometimes it's also called the face of the number Z. So all these are just a very brief review of something probably you know about the complex number. For each complex number, there is another number which we call the conjugate of the complex number. So let's say z is a plus ib. Then the conjugate of z, which we denote by putting a horizontal line on top of z, will be a minus ib. In the polar coordinate, the real axis and the imaginary axis. If the z is here, then the conjugate of z would be the point that's symmetric to z and at the real axis. So you can think, instead of rotating this angle up, and you rotate the same angle but down, and you will find the conjugate of z. Okay, some obvious example. If z is 4 plus 3i, then the conjugate of z is 4 minus 3i. We can make operations with complex numbers. First, the sum of two complex numbers. Let's say we have a number z is a plus ib, and z prime is a prime plus ib prime, a different number. Then if you want to add them up, z plus z prime, that's the z and that's the z prime. How do you add them up? Well, you will add up the two real parts and form the real parts of the sum, and you add up the two imaginary parts, and that forms the imaginary part of the sum. Okay, so a quick example. So let's say z is 2 minus 3i and z prime is 5 plus 6i. I want to add them up. Well, so I'll take 2 and the 5, and then it's 7. That will be the real part. And then I take negative 3 and 6, add them up, I get 3i. That's the imaginary part. We can also take product of two complex numbers. Let's say again we have two complex numbers, z and z prime. And here we need to utilize the identity. This I here satisfies the identity that I square equals negative 1. Okay, and then we can define the product of two complex numbers. So z times z prime here. And we will treat these expressions just as two separate numbers times the sum of two separate numbers. And then we can expand this and open this up. You can have a times a prime, and then plus a times ib prime. And then you will have ib times a prime, and then the final term is ib times ib prime. And there you will get the I square, and you will put that into minus 1. And this will be joining the real part, and the imaginary part is these two products and these two products, and that give you this. Okay. So a quick example would be, say that's my z prime, and I want to compute z times z prime, and I've put in the numbers for z and z prime, and now I can open this up. I can distribute 2 plus 3i times 1 first, then I will get 2 plus 3i. Then I will multiply this by the negative I, so I will get negative 2i from here, and then here I will have negative 3i square. And then I square is negative 1, so this becomes positive 3, and join together with the 2, I get 5 as my real part, and the imaginary part will be 3 minus 2, and is I. And the product of the two numbers viewed in the polar coordinate is very interesting. So we have that the modulus of the product is exactly the product of the moduli. So meaning that z times z prime, the modulus of that, would equal to the modulus of z times the modulus of z prime. Furthermore, the argument of the product is actually the sum of the argument of z and z prime. Okay, so let's look at it in the picture. What does it mean? So let's say this is z, and it has a modulus, let's say, about something bigger than 1, and then it has an angle theta going there. And then you have another number z prime, which is down here with the angle, a negative angle, and then z prime is shorter. Okay, and then z times z prime will have modulus the sum of these two. So this theta looks like it is bigger than the negative of this theta prime. So theta plus theta prime would be some positive angle here. And then the modulus of this product here, z times z prime, this length here is the product of this length times this length. Okay, so let's take an example. So kind of following this graph here. So now z is 2 plus 3i. So that's my z, 2 and 3i. And my z prime is 1 minus I, so that's my z prime is 1 here, negative 1 here. So let's first find out modulus of z, which is square root of 4 plus 9 is root of 13. And then z prime, the modulus of that is square root of 1 plus 1, which is 2. And then what is the modulus of z times z prime? Well, so we already calculated z times z prime, which is 5 plus I. So this will give me 5 squared plus 1 squared, so it's square root of 26. Okay, so let's verify the property of the moduli. So let's look at the modulus of z times the modulus of z prime. That will be square root of 13 and then square root of 2, and that gives you square root of 26, which is the same as that number. Okay, so we show in this example that this identity holds. Now let's look at some properties of the conjugate. So remember, the conjugate is a point here that you flip it in the other direction of the real axis. That's the conjugate. Okay, so now if you have two numbers, z1, z2, and they're complex numbers, then their complex conjugate satisfy the following. z1 conjugate plus z2 conjugate equal z1 plus z2 conjugate. So the conjugate of the sum is the sum of the conjugate. Furthermore, the conjugate of the product is the product of the conjugate. And then for a complex number, the real and the imaginary part of it satisfy the following identity. So the real part of z equals the real part of z plus z conjugate divided by 2. And the imaginary part of z will be z minus the z conjugate divided by 2i. Okay, this follows immediately from the definition. Okay, so let's check with an example some of the properties we mentioned. So let's say I have a number z1 and another z2. They're given here. And then let's write out the conjugate of it. That is, change the sign of the imaginary part. Okay, let's check the conjugate of the sum is the sum of the conjugate. So if we add up z1 plus z2, you can add this up, you get 7 plus 4i. And then let's look at the sum of the conjugate, the z1 z1 conjugate plus z2 conjugate, then you know you get 7 here. You get -1, -3, that's -4i. And comparing this number to that number, and we see that that is exactly the conjugate of this. So that's that. Now let's verify the same property for the product. Okay, so let's take a product z1 times z2, and it's this one times that one, and then you know that the real part will be the product of the real part, 2 times 5, and minus the product of the imaginary part, because the square of I give you -1, so it's -3. And then the imaginary part will be the cross product, so 2 times 3, which is 6, plus 5 times 1, which is 5, and that's the real imaginary part. Okay, so you get 7 plus 11i. Okay, and then let's work out the product of z1 conjugate and z2 conjugate. This number, what do we have? Well, very similar. So the real part will be 10 minus 3 here, and then the imaginary part will be -6 minus 5 here. So I get 7 minus 11i. And compare this to that, I see that this is this number's complex conjugate. Okay, so we verified that first property. Now let's look at the inverse of a complex number. You have a complex number, z equaled a plus ib. What is the inverse of it? Okay, so the inverse of it is just this fractional number 1 over z, and we can write out is 1 over a plus ib. And what one can do to figure out what is the real and imaginary part of this number is to multiply both the numerator and the denominator by the complex conjugate of this number, which is a minus ib. And we multiply it on both. And then the numerator is kept, and the denominator becomes a square minus I square b square, and then I square is -1, so you get a square plus b square, which is a real number. So we can write out the real part, which will be a over this denominator, and the imaginary part will be the I here. You take it out, and then you get -b over that number, -b over the number. And we see that for the z inverse, the modulus of z inverse is the inverse of the modulus of z. And about the argument, if theta is the argument of z, and then for z inverse, the argument becomes negative theta. Okay, a quick example. Let's say, take the z number is 3 plus 4i. Let's find its inverse. And then we multiply both the numerator and denominator with the complex conjugate, 3 minus 4i. And then the denominator becomes 3 square plus 4 square, and which is 25. So the real part is 3 over 25. And the imaginary part is -4 over 25. And we can compute the modulus of z, which is 3 square plus 4 square and square root. So it's 25 square root, it's 5. And then we can also compute the modulus of z inverse. We have the real part and we have the imaginary part. So it's a square root of this square plus that square. And if you work out, it's a square root of 1 over 25, and which is 1/5. And we see that. And it's just the z modulus inverse. Okay, so that's the property we stated on the previous page. So we verified it with this simple example. Okay, so let's take a break. I hope all these are familiar to you. And in the second half, we will review a few more things. Okay, so I'll see you then.